Hello, I'm Florian Schreck, Professor for Experimental Quantum Physics at the University of Amsterdam. Welcome to the labs of the Quantum Gases and Quantum Information Group. In our lab, we cool atoms from the usual hundreds of meters per second that they have down to centimeters per second velocity. And that gives us then full control over our atoms, which we can exploit for quantum simulation, quantum computing, or quantum sensing. To cool our atoms to these low temperatures, we use very special types of fridges, such as the one you see here. It's a vacuum chamber. On one side, we have an oven where we heat strontium to 500 degrees Celsius, where atoms evaporate and form an atomic beam flying with hundreds of meters per second through the vacuum chamber. From the other side, we shoot a laser beam against these atoms. And when the atoms scatter light, they slow down. And with additional laser beams, we push them to the center of our vacuum chamber. And you can now see a cloud of many strontium atoms levitated against gravity in our vacuum chamber and cooled down to millikelvin temperatures. And to cool and manipulate our atoms, we use lasers of many different colors. And by the way, how a magneto-optical trap works was first explained by the group of Claude Cohen-Tanucci in Paris. And he obtained the Nobel Prize for this achievement. And if you cool the atoms to this ultra-cold regime, they don't only behave like particles, but also like waves. And we have used this to create the first continuous atom laser in the world. And then in the future, we want to use our technology to improve quantum sensors. For example, sensors that measure acceleration, rotation, or gravity, or also clocks that measure the flow of time. And in this machine, we prepare an array of single strontium atoms and use them as quantum bits. In this way, we can build a quantum computer that for certain problems is vastly more powerful than any classical computer. And all these ultra-cold quantum gas devices can be very beneficial for society. For example, ultra-cold quantum sensors can be used to explore the underground to see if a magma chamber of a volcano fills up, if water tables change, or we can use them to synchronize telecom networks or perform terrestrial navigation. With quantum computers, we hope to be able to solve complicated quantum chemistry and optimization problems. And within the Dutch Quantum Delta NL and the European Quantum Flagship, we are working together with companies and startups to render these machines much more compact and reliable. Among others, we are working with French companies such as Pascual, Nixail, and French research groups from Strasbourg and Paris. By creating robust quantum sensors and quantum computers, we can bring all the advantages to society.
Quantum Delta NL is the national ecosystem for excellence in quantum innovation. It brings together some of the strongest groups in the field in 5 major hubs. Amsterdam is well embedded in all Quantum Delta programs. For example, as part of the Catalyst program on quantum sensing applications, the Amsterdam team is developing the ultra-cold quantum sensing testbed. In addition, within the Catalyst program on quantum computing and simulation, the group is building a quantum computer in collaboration with Eindhoven University of Technology.